you are going to get a very nice circle, and it will also tell you that was not a chance event that these things are together. The probability that this could happen by chance is less than 1 in 1,000. Okay, so you can statistically also say yes, it's a serious pattern. Okay, so this is sort of an example of spatial statistics kind of analysis of patterns or hotspots of concentration in space. So this is the output of actually SAT scan, and you can kind of see some of the p-values here. It will give you something very powerful. Okay. Now, same kind of analysis now is done not only for cancer. To make calculations simple, exactly. Because these theories are before computers came along, and they had to calculate everything by hand, right? In fact, Britishers, they hired, their biggest computing resource were the clerks in Chennai, Madras. They had hundreds of people computing Pearsall correlation coefficient. And this independence assumption makes your computation very easy. Then in one scan, you can compute correlation coefficient, linear regression. But look what they gave up for calculation, right? So as the computers become powerful, you don't have to do that anymore. In last 20 years, computers have become powerful enough that you can use these new models, and you should be. All right. So again, I'm not going to name these theories, but hopefully, since Gian Jnu is such a broad department, is there any department which teaches spatial statistics, either in public health or in epidemiology or geography and so on? You probably have somebody on campus teaching, just that you may not know which department it is. It's a very broad campus. But you'll see there are books and a lot of people are teaching. Just to give you an example of how these models may change. The first one many of us recognize, right? Linear regression. It says that a property at a location, it depends on other properties on the same location in a linear manner. Okay. Here is a change of that where we have added auto-regression. Okay? And this model is saying that a property at a location partially depends on other properties on that location, but it partially depends on the same property in the neighborhood. Okay? So this is sort of your spatial auto-regression model. It came from regional economics. So equation-wise, it's pretty, it's reasonable. And again, if you want an interpretation, think of it this way. So many of you probably remember Hurricane Katrina about 10 years ago, which flooded New Orleans, many of you. Now, interestingly, there is a very old neighborhood in New Orleans called French Quarters. It's a very touristy place. And if you look at the map of flooding, it was not flooded. Okay? So originally when people came to New Orleans, they settled on the best land, most protected and nice land, right? And that was this turtle. Then more people came and they didn't have the good land. What did they do? They lived near other people who were already there, and that's this turtle. Okay? So people, if you think about where they live, where they build the house, it's not because the land is the best. It may be because they are near other land which is good. Okay? And this happens in many, many phenomena. Okay? So equation is intuitive, but the computation is horrendous. And that's what tells you why people didn't do it in the beginning. Now if I want to estimate this rho and beta, I have to do a maximum likelihood computation, and this is a big determinant. And all I'm saying is computation is more expensive. They couldn't do it 100 years ago, but now we can do it well, and now we are ready to use these models. That's all. Okay. So computer science has made some contribution to society in this space. Okay. Okay, and there are other patterns you can also detect. One pattern we'll talk about on day 4 in spatial data mining is this collocation pattern. Okay. So I'll just give you an intuitive feeling of this pattern. So here I am showing a map, and this is okay. That's good. I heard also about green. What was the pattern? Could you repeat? And green and what? Green and blue. Okay, how many see green and blue together?
First initially we had white and blue going together.
Okay, so it will repeat. There's 15 frames, so you can kind of see. All right. But this is a little bit harder as things are moving. Yeah. So again, here that the algorithm finds blue and red as the highest co-occurring, and if you go further, you will probably find some more shades. So anyway, these are the kinds of patterns we can find. Now let me maybe take you one step further to some of the current research. So we are going back to public health. Nowadays, we do not wait for number of deaths that happened in London cholera 1854. So Gian Jnu in some sense was lucky because there were hundreds of deaths. When he made the map was so dense he couldn't miss the pattern. Okay, what happens today? Okay, so here is an example. So this is Legionnaire disease in Manhattan, and just a year ago. And you're seeing these light colored dots is where people became ill. They didn't die, but it's sort of like asthma, it's a disease of respiratory system. So this is where all the people in the red, the dots, people are sick. Legionnaire disease is well known to be caused by water towers. So tall buildings, hotels, they have cooling towers for water, and they sometimes get this bacteria. And through the spray and so on, people who are passing by get this bacteria. So these are sort of, the red ones are the hotel towers which were suspect. So let me first ask you, suppose you look at your spatial knowledge and tell me which red square are you going to test first, if you could test only one. Okay, how many think opera? Quite a few, good. So you have a very nice intuition, and that's why actually usually first maps are used. People will put push pins on a map and they will eyeball it. And that is the one which was tested and actually found. Now, this is going to show you some limitation of SAT scan, because the data is so sparse. If I ran SAT scan, I'm going to get these clusters which are statistically significant, and it's only 1 and 2 are statistically significant, p-value below 0.05. Third is not. Okay? But notice that Opera House is neither contained in 2 nor in 1. Okay? So, because the data is so sparse, you have to start developing some new techniques. Okay? So one of the research projects that we are working on, because of a slightly different application, looks for rings rather than circles. Okay? And these rings, again, same statistical measure, log likelihood ratio and p-value, and you notice that it puts the ring right around the Opera House. This pattern actually comes from environmental criminology, where serial criminals are known to have very interesting behavior. They don't commit crime next to their home because their neighbors know them and they can turn them in. But they usually don't go very far because of transportation cost. So for serial criminal, the footprint of crime location is known to be a donut hole pattern. So the research project actually started from there, and it turns out for the tall towers or chimneys, you have a similar effect because it doesn't drop things right next to it. The wind carries it a little bit further, and you get a ring pattern like this. So some examples. Okay. So essentially in this space, we are kind of enriching it. It's no longer just simple mathematically looking for circles and so on, but we are looking at geographic concepts or social science theories to try to pinpoint what the pattern should be, okay? And develop things based on those notions. Like here is one from environmental criminology. You're looking for donut hole pattern. And if you're in urban areas, it's interesting to actually look for things like rivers or roads. So I'll show you one other example. Here are pedestrian fatalities in Orlando. These little dots are where you had a vehicle and a pedestrian crash. If I use something like SAT scan or K-means, it will try to fit ellipses to that, and you kind of see, they give you some description, but it's much more natural to have linear hotspots to describe this data. Right? So these are some of the new trends that are happening. These mathematical theory, because spatial statistics at the end of the day again is probability theory, isotropic Euclidean space. Does not understand a lot of concepts from geography and social sciences. And the new trend is to try to bring the two space together. Okay, so again pause here for a minute, see any quick questions on this whole area called spatial statistics and spatial data mining. And I will also tell you that when the communications of the CSCM article, the reviewers agreed that GPS has had a lot of influence on society, remote sensing has had influence, location-based services had influence. But they argued a lot saying, well, spatial statistics probably hasn't had as much influence, so you shouldn't be talking about it so much. And we had to go and list a lot of other applications like weather forecasting, public health, and number of those to try to make the case that it indeed is equally powerful idea and we should all be learning. So, but again, day 4 we will go a lot more into it. Any quick questions, issues, and so on.
In the SAR, the matrix, the
Right.
neighborhood matrix that
Right.
was there,
Yeah.
that would depend actually on the number of, let's say, of cells or locations or pixels that we consider as, so it's not going to be large really.
So if you think about
It can be controllable.
it can be controllable, but so it depends on, suppose you have n pixels, then W is a n by n matrix, but it's very sparse, you're right, because typically we use simple neighborhood, 4 neighbor, 8 neighbor,
Yeah.
so the number of non-zero entries would be still linear in n. But the problem from computer science perspective is the following. So in computer science, if you work with sparse matrix algorithms, the only way to get efficiency is if the sparse matrix is banded. And this is not, the band is very broad here. So W, I said, it doesn't look that big here, but if you think about again spatial data set, if I look at satellite imagery, how many of us have worked with the imagery? A few. So how many pixels in a typical satellite image? Millions of pixels, right? So W is now million by million. Okay, so 10 raised to 12, that will bring average computers to their knees, right? But it's not just that, it's the determinant. This is the determinant of that bigger matrix. And turns out that people who do linear algebra and so on, most of them were so focused on partial differential equations that they assume that they will never have to compute the determinant and all eigenvalues. They always were looking for just a few eigenvalues. So this is a horrid, it's a big matrix, and then determinant confounds, at least the colleagues I have talked to in linear algebra and numerical analysis. But the reason I also bring it up is to say computer scientists, they still have work to do here. Okay. But if you have smaller data sets, if you have a few thousand points, okay, then this can be done very well. You have MATLAB routines to do it. It's no problem. Okay. But if you have 1 million point, you still would need partnership with the computer science department and a researcher. And hopefully, that's another purpose of this. You want to bring ideas from both sides. Okay? So computer science still has a role to play in this space. But if you have a 1,000 point problem, there are software is around. You don't have to worry as much. Okay? Any other questions, thoughts? And again, on day 4, we'll get into this more. Alright, so let's go look at one other aspect of this space. Yeah. We can break and then continue afterwards. That's yeah. Sure. So let's break here, and when we come back, it's a good point, then we'll look at 3 more things.